Good morning, my friends. My name is Yunqing Li. I'm glad to share my research named A Big Data Evaluation of Urban Street Walkability using Deep Learning and Environmental Sensors. Now I will introduce my research briefly. During the past few years, the fields of urban planning, transport, and public health have been drawn together by their common interests in walkability. This call for improving street walkability is not the first attempt historically. However, nearly all urban designers and researchers at the time depend on the observation of walking activity and logical reasoning, rather than measure or evaluate walkability numerically. The emergent deep learning algorithms for processing street view images integrated with GIS analysis and environmental sensors shed light on evaluating the street walkability quantitatively. Since the beginning of the 21st century, walking audit tool emerges, and some scholars uses Google Street View and semantic segmentation to measure the street walkability, which solve the shortcomings of insufficient sample size and inconsistent scale of manual evaluation. Based on the review presented previously, this paper builds a methodology to evaluate the walkability of urban street (WOUS) for both physical and perceived results. This figure shows the framework of the study. There are two parts of the walkability evaluation. One is automatic evaluation of physical WOUS. The other is subjective evaluation of the perceived WOUS. First, the physical one is done by selecting representative indicators and then using automatic approach for analyzing. There are 7 typical indicators. These indicators are selected according to the literature review and their capacity as measurable aspects. GIS, semantic segmentations, and field measurement are used for data analyzing. After this, these 7 indicators results are combined into one index using analytical hierarchy process (AHP) and questionnaire to represent the physical WOUS. Next is the perceived WOUS evaluation, which is represented by the score of willingness of street users to walk in the space. This study used feasibility, accessibility, safety, comfort, and pleasurability as its evaluation standards. Finally, compare the physical WOS with the perceived WOS of the streets as a verification process. The approach is then applied to the streets around Osaka University Suita campus. For the physical WOS evaluation, first, POI data, street view image, traffic flow data, environmental data are collected from Google Map, Google Street View, panoramic camera, and sensors, respectively. To achieve an auto-calculated method, we integrated several tools for these 7 indicators. We used GIS analysis, semantic segmentation, field measurement for this indicator evaluation. All the data and analyzing results were imported into QGIS with coordinate information. To summarize the physical WOUS into one index, AHP was used, which can help to calculate the weighting of each indicators using a pairwise comparison by questionnaire. Table 1 shows the physical WS evaluation indicator weightings results. With these weightings, the 7 indicator results are able to combine into one index, and they can get a physical WS result score from 1 to 5. Second is the perceived WS evaluation. In this study, the willingness to walk is scored by urban planning, and to measure the overall perceived WS directly based on the hierarchy of walking needs model. 4 raters were invited to comprehensively measure the WS by field survey, giving a score from 1 to 5. This figure shows the sample street view images for different walking willingness scores. Here comes the result. This figure shows the 7 physical features results separately. It can be concluded that the streets near the large public service facilities have better physical WUS. These areas often have better locations and spatial qualities, and gather a relatively high density people which need to take more consideration of street walkability. Due to higher traffic flow and environmental noise, the walkability of municipal streets is significantly lower than the streets on campus. With AHP approach, Figure 4 shows the final 7 aspects physical WS index results. The average score is 2.26. High score areas are around these places. Figure 5 shows the overall perceived walking willingness score of streets. The average score is 2.67. Taking the perceived WS as the benchmark, there is a relatively fair agreement as well as a discrepancy between perceived and physical WS. The results are verified by comparing high score areas with site visits. We found that the index could tell the feasibility and accessibility but could not reflect the comprehensive walkability. The main contribution factor to the difference is the ignorance of some aspects related to walking pleasurability and comfort, such as the level of aesthetic appeal and street slope. While these factors are important indicators for subjective evaluation, they are missing from automated evaluation, leaving a gap for further research. Finally, the conclusion. This study proposed an evaluation framework for walkability of urban streets, including physical and perceived WS. The first was calculated automatically with the support of QGIS, semantic segmentation, and AHP, while the latter were achieved quantitatively through weighting system based on hierarchy of walking needs model. Thank you for your attention.